Hello everyone, I want to welcome you to this talk about the DeepSeek Moment. My name is Konstantin. You can find me on X at Hallerite, and this is a talk that was held yesterday on February 5th, 2025 in the Agentic Data Research Group hosted by CAMEL-AI, and there were some technical difficulties. So we decided that I would record this myself again so that we can have an uploaded version of it that is a more smooth viewing experience for you. So here we are. And in this talk, I want to talk about the state of AI at the moment with regards to what happened with DeepSeek. So let's begin by talking about the Sputnik moment. In October 4th, 1957, the Soviet Union launched Sputnik 1, which was the first artificial satellite that was ever successfully launched into our orbit. And this was quite a huge success, especially because no one would have expected the Soviet Union, which many viewed as a backwater, to achieve such a feat of engineering. And as a matter of fact, the US were totally shocked and caught by surprise. It marked the beginning of the space race amongst widespread panic that the Soviets might be much more powerful than previously anticipated. And there was also the fear that if they can get to space first and can get a dominance there, they can launch nuclear warheads from space. And that would, of course, be very difficult to defend against if you don't have a space program that works. So the US just basically 1 year later created NASA, which is the successor of NASA, which was a space agency that also tried to launch a satellite but failed repeatedly. And it was also the moment where the US started funding STEM education and space research a lot more. Then, 3 years later, Yuri Gagarin, another Soviet, became the first human to ever be in space in 1961. And just 4 years later, Alexei Leonov was the first person to ever do a spacewalk. So that was basically Soviet dominance at this point. The US had been trailing behind. And then 4 years later, the US finally definitely caught up with their Apollo 11. They launched a rocket, and 4 days later, they landed on the moon, and that concludes the space race, at least how it is usually, that's how the narrative usually goes. And it definitely established the United States and the Soviet Union as at least equals, with the United States even leading now, since they were the only ones who were capable of landing someone on the moon and getting them back. And why am I telling you this? Well, just recently, DeepSeek released R1. And R1 blew everyone away. Just directly after its release, among the LLM enjoyers on certain parts of Twitter, or X as it's now called, R1 became a hot topic, and it became what we were all talking about all the time. We were digging into the technical report, we were testing it, evaluating it on different benchmarks, and we were just in awe. And just 6 days later, and this is the big surprise, it reached the #1 spot on the most downloaded apps in this week on the App Store. And that was something that none of us would have expected the days before, because we knew that, yeah, it's a significant release and it's the best open source model ever released. But it was never the case that, let's say, normal people, normies, how we call them, ever caught up to it, right? They are not using Claude like we are. Maybe some people in San Francisco are, but they basically just use the free version of ChatGPT. And the fact that they downloaded DeepSeek and they heard of it, it was quite something. And just a day later, remember 26th of January was a Sunday, so the market was closed. The day after, major tech stocks took a large hit, and in total, $1 trillion were wiped in market value. And I think it was about 400 billion just for Nvidia, which dropped 17%. We can talk about whether that is justified or not, but if I recall correctly, that was the largest wipeout in the history of the US market for just a single stock in one day. So yeah, this led to even more panic, and people, famous people in the AI scene, policymakers, but also venture capitalists and tech CEOs from the US were started calling for stricter export controls. Others were casting doubt about the legitimacy of the costs that DeepSeek reported, which were 5.5 million, which again, I want to emphasize was the cost for the successful run at the end, which does not include the salaries of the researchers, many failed runs, the capital expenditure to get the hardware, and it's also what they project it would have costed if they rented the GPUs at a reasonable price, the GPUs that they already bought. So in fact, the run itself was cheaper for them, but of course there were a lot of other factors that made it more expensive if you factor those in, that led up to this run. And today, okay, it's not the 5th of February, but close enough, that was yesterday. Basically everyone is trying to reproduce R1 and build upon it. Many people are experimenting with the COTs that R1 releases, and it's quite interesting because it seems like there's nothing that people talk about nowadays except for R1. Well, at least it's quite significant in the AI scene. So I want to talk about quickly Jevons paradox, because that is something that also the CEO of Microsoft stated and posted on X about regarding the drop of Nvidia. And the quote by Stanley Jevons goes something like, "It is a confusion of ideas to suppose that the economical use of fuel is equivalent to diminished consumption. The very contrary is the truth." And he said that in a time where the industrialization was still ongoing, and there was a widespread belief that the coal would be depleted and then that the industrialization would stop. And so it was important to people that we were getting like more efficient machines that have a better utilization of coal, that they can extract more energy or are in general more efficient, don't emit that much energy as heat. And Jevons just came out and predicted, he reasoned from first principles that people would not stop using coal. I mean, they would not use less coal if the machines that run on coal are going to become more efficient. Instead, they're just going to be using more machines. And as a matter of fact, the demand for coal may even rise, even though the efficiency of the machines is rising and they need less coal individually, right? There's just going to be more machines. And this actually did happen. And it's quite analogously to intelligence. So intelligence is a bit different. It's not exactly like a resource that can be depleted like this, but it is definitely associated with a cost. And to get this intelligence, to get these LLMs, they need to run on hardware, right? So maybe the coal in this case could be something like an NVIDIA GPU or a TPU. And R1 changes the game because it makes intelligence more affordable, and which is kind of the same as making it more efficient, because we can use less hardware for more intelligence, so to speak. And that is one of the reasons that people were shorting NVIDIA and selling their shares, because they believed that this gain in efficiency and would basically be a bear signal for NVIDIA GPUs, which is of course contra to Jevons paradox. And as I said, more ventures now become economically viable because the API cost, but also the ability to self-host makes the intelligence more affordable. So people are gonna start using LLMs for tasks that they were prohibitively expensive. And also, I'd like to note that since it's open weight, you can host it yourself, or you can choose a provider that hosts it most cheaply. And it's also MIT licensed. And in case you're not familiar, the MIT license is a very permissive license that allows it to be used in basically for anything. It's quite a strong license. And that also means for the builders, not only for the researchers, but also for people trying to build a startup, that they can build a lot of cool stuff on top of R1 now, and they don't have to worry about vendor lock-in or something like that. So let's talk about how R1 was trained. In the technical report, they talk about two models. They talk about DeepSeek R1.0 and DeepSeek R1, which is the one that they offer via their web app and API. And DeepSeek R1.0 is just the base model DeepSeek V3, which is like their flagship model. And on top of that, they just do reinforcement learning with a verifiable reward. So not reinforcement learning from human feedback, but something else, which we're going to get to. They just do it on math and coding mostly. And yeah, for DeepSeek R1, they found that the model has like that the DeepSeek R1.0 model has a few things that we don't want. So for example, in the reasoning traces, there's language mixing and some other weird stuff that is, that we don't want, that makes it look a lot more awkward than it should be. And so they came up with DeepSeek R1, which takes the base model, the DeepSeek V3, it adds a cold start, is what they call it, cold start SFT. So they do some supervised fine-tuning on reasoning traces. They then do the same reinforcement learning that they did in the DeepSeek R1.0 for the DeepSeek R1.0 model. And after that, they do some more SFT, which is, however, rejection sampled. In some way, they don't talk about the details exactly, they just outline it. And then in the end, they do some more reinforcement learning, this time on more domains than just code and math. So you can expect that it is probably also in instruction, like with human preferences, stuff like that. Though they don't go into too much detail in that end. So you can see DeepSeek R1 is quite the multi-stage process. Like getting DeepSeek R1 is quite difficult. Or let's say it takes multiple steps to go from DeepSeek V3 to DeepSeek R1. It's much more than just the reinforcement learning, which is important to keep in mind. But then again, reinforcement learning plays a big role, and the question naturally arises, why did reinforcement learning work now all of a sudden? So why do we get these insane results with reinforcement learning that surely are so obvious? Like these techniques are so obvious. Why did no one else come up with it? Why didn't OpenAI or Anthropic or whatever come up with it? And the thing is that we obviously don't know how O1, like OpenAI's reasoning model was trained, but it is definitely possible that they also experimented with reinforcement learning. But the DeepSeek R1 introduces a few techniques that make it quite distinct from anything that we've ever seen before, at least in the open source space where we know how it was trained. So for example, we do GRPO instead of PPO for the reinforcement learning, which is a reinforcement learning algorithm that builds on top of PPO. We're gonna get into that. Then there's also a rules-based non-learnable reward model. So you don't have something like in reinforcement learning from human feedback where we train the reward model from human preferences, and instead we just give it some rules, ideally in a verifiable domain, so that one rule can be, is the output of the LLM correct? And then we just do normal reinforcement learning on top of that. And lastly, what might also be a reason is that we now have a stronger base model to start on. So there are some people who think that this would not have been possible if the base model that we start doing our reinforcement learning on would have been something like GPT-2. while others are claiming that they see improvement even on very, very old and weak models. So I guess it remains to be seen what is the case. And in this talk, we're definitely going to take a look at this RL that I highlighted, so the one with the verifiable reward. We're going to look at GRPO, which is the algorithm that is used to do the RL training. We're also going to look at PPO, because if you understand PPO, then understanding GRPO, which has quite the intimidating math formula, is quite simple. You're going to see that if you understand PPO, GRPO is basically just a simple extension on top of it. Afterwards, we're also going to take a look at a rules-based reward. I coded up a very simple one, and yeah, I'm looking forward to showing it to you so you can understand how this might look like. Okay, so let's begin with PPO. PPO is an on-policy, policy gradient reinforcement learning algorithm, and it is the de facto standard for most intents and purposes. If you have to deal with reinforcement learning, chances are you're gonna have to deal with PPO. The biggest exception that comes to mind is robotics, where they use soft actor critic instead of PPO, though soft actor critic is not that different. If you understand PPO, understanding soft actor critic is pretty straightforward. And that was also the algorithm that OpenAI used to beat, quote unquote, DOTA. I say beat I put the beat in quotation marks because it is quite a difficult game to beat, and they simplified it a lot, and they had to do some other tricks which I'm not going to get into. So I wouldn't call it beating the game, but they definitely performed very, very well with their OpenAI 5. And let's maybe circle back to the first bullet point and talk about on-policy and policy gradient, because maybe you're not familiar with reinforcement learning. So in reinforcement learning, we have a policy that we want to train, or rather, let's say, especially in the policy gradient reinforcement learning algorithms, we represent a policy specifically or explicitly, as a neural network or some other learnable function. And we try to find the parameters that maximize the expected reward. So you always are in a state when doing reinforcement learning, and your agent can perform an action. And he samples the action from the policy conditioned on the state that we're currently in. And the policy gradient method is just a method that directly optimizes this policy by taking the gradient. So yeah, there are also other methods like value-based methods, DQNs and so on, but those are not policy gradient-based methods. There you extract the policy another way. But that doesn't really matter for now. And on policy, it just means that whenever we do our update on our policy, we always take fresh samples from the environment. We don't take samples or rollouts, as they're called, so full trajectories where we basically used our policy to collect some experience. We always get fresh ones. We don't save them and reuse them, even though the policy that we currently have was not the one that produced them. We just get new ones every time we do our update step. Right. So that's the overview of PPO. Let's look at the formula. It looks a bit intimidating, but don't worry. So we have this j of theta. So we can see that j is the objective function, and it depends on theta, while theta are, of course, the parameters in our neural net that we can optimize. And this objective function is just an expectation over some objective. And in general, it's the expected reward. But in this case, it's a surrogate. It's not exactly that. It's an expectation over the minimum of these two terms. Okay, so what are they? Well, let's begin with this RT. It is not the reward, as you may have thought, but it's the ratio. As a matter of fact, it's the probability ratio. It comes from importance sampling, if you want to look that up. And the idea is that we should compare the current policy that we have, that is fixed, right, which is pi theta old, with a new policy that we try to find. So this is basically the one that we're optimizing over. So pi theta. And you can basically, we're gonna look at an example later on, and it's gonna become more clear. But at the moment, just realize that this is just a ratio between two probability distributions. And of course, you can't take a ratio over two functions, or maybe you can in some space. But in this case, of course, we always get a number between 0 and 1, just probabilities, because we sample it with an action given a state. Then this A hat is the advantage estimate, and the advantage estimate is just an estimate of the advantage. So that's why the hat is there. It's because it's an estimate, and the advantage itself is just a number that tells us how much better taking this action in the state that we're in is compared to the average action that we could take. And yeah, so basically, if the advantage is positive, that means that the advantage for this action in the state is, so if the advantage of an action in a state is positive, then that means that taking this action in the state is better than the average action that we could take in the state. And the other part in the minimum is something that contains this clip function, and the clip function, which is the clip of the ratio 1 minus epsilon and 1 plus epsilon. This, so you can think of the first argument as the one that we are evaluating, and we want to clip it to be either the lower bound, which is 1 minus epsilon, or the upper bound, 1 plus epsilon, in case that it is below or above these bounds, or otherwise we just choose RT itself, so we don't do anything. So this just means that RT has a maximum and a minimum, so it's bounded for sure, and the bounds are known to us. And we actually decide those bounds by choosing a hyperparameter, which is this epsilon, which is the clipping threshold. And you can think of this as controlling the exploration and the exploitation, because a higher epsilon means that the bounds are, well, the lower bound is lower, the upper bound is larger, so the range gets bigger and we do more exploration. That's how you can think about it. Right. So let's do a concrete example. In this case, we have a positive ratio. So we assume that the new policy that we're currently looking at would have a probability of 0.12 for the action in this state, while the old policy would give us 0.1. And that would be a probability ratio of 1.2, of course. And let's assume that the advantage is positive, so taking this action in this state is better, it's a bit better. And lastly, let's, for simplicity's sake, assume that the clipping threshold is 1.1. Okay. Since we have now fixed a probability ratio, we don't take the expectation. This is just one step. It's just for simplicity's sake. Okay, so let's look at this part that is highlighted in red. This is just the probability ratio times the advantage, which is, as you may have guessed, just 0.6. It's 1.2 times 0.5, so 0.6. And let's evaluate this clip part. Remember that the epsilon is 0.1, so we get, so clip basically is fed in the arguments 1.2, 0.9, and 1.1. And since 1.2 is bigger than the upper bound 1.1, we need to clip it. So we just output the upper bound. We don't output 1.2, we just output the upper bound, which is 1.1. So this evaluates to 1.1. And now lastly, we still need to multiply that by the advantage. And the advantage is 0.5. So this is going to evaluate to 0.55. Now we still have to take the minimum, and of course 0.55 is the solution for that. Okay. So what are we doing really? Well, clipping ensures that we only update at all if the ratio is significant. So if it is beyond the lower or upper bound. And that is because otherwise the gradient is going to be 0 and we're not going to have any loss. Okay. On the other hand, clipping also prevents updates that are too drastic. Because what clipping does is, it basically says that the update step can only be at most, that the advantage can only at most be multiplied by the lower bound or the upper bound. Nothing that is beyond that, which increases the stability quite a lot because we don't do updates that are too big. And lastly, this min operator enforces a more conservative policy improvement. It basically tells us, okay, this is only the worst of the two, right? It only improves by this much if we take this new policy. And it's just a bit pessimistic and also helps us prevent too drastic updates. Okay, that was PPO, and PPO is used with LLMs for quite some time now, most famously with the reinforcement learning from human feedback. And well, as you may have noticed, LLMs are quite large. They have a lot of parameters. They are over-parameterized even. And we fine-tune only on a very small data set when we do our RLHF compared to the pre-training. So the tokens that we fine-tune on, they're not that many compared to the corpus for like the trillions of tokens that we trained on. Okay, well, that means that the base model probably learned some meaningful representations of the world. It has an implicit world model, and it learned the structure of language. And we don't want to lobotomize it by just deviating too far from that just to maximize some reward. So what we do is we further restrict the policy updates by adding a KL divergence term between the base model before we started our reinforcement learning and the current policy that we are evaluating. And that further restricts the updates or the size of the updates that we're going to do. And the equation is thus the same as above, but we also have this KL divergence term that prevents too drastic updates and deviations from the original base model. Okay, and this is modulated by this beta hyperparameter. The bigger this is, the more it's going to force the optimization to not deviate too much from the original reference policy or the reference model. Okay. Let's talk about GRPO now, which you can think of as the PPO alternative for those who are GPU poor, which DeepSeek is, relatively speaking. And necessity is the mother of all inventions, so they invented an algorithm that allows them to still get a lot of training done while needing less memory and compute. And they call that group relative policy optimization. And the innovation is to approximate the critic, which is part of the advantage estimation with normal PPO, with just doing a few rollouts. We're going to take a look at that very soon. So don't worry if you don't understand what this means now. And approximating the critic, which is usually, in the case of PPO, a language model with a validation head on top, saves, of course, a lot of memory since LLMs take a lot of memory just for inference. But since you also have to train the critic each step, we save even more because training LLMs, of course, is even more memory and compute intensive, right? Because you have the optimizer states and the gradients as well. Okay. So this is this is basically the innovation with GRPO. And GRPO has a pretty scary formula if you look at it, right? The objective function of GRPO is pretty scary. It doesn't even fit in one line. Trust me, I tried. Yeah, but we can break it down and it's going to become much simpler than you probably had anticipated. So let's just notice for now that this term, this minimum term, is just PPO, right? You should recognize this. It's basically the same. It is exactly the same, actually. And that is because GRPO is just an extension of PPO, or a simplification of it even. And the only question is, where do we get these advantages? Well, we're going to answer that in a second. Before we do that, let's look at what we are taking the expectation over. And we're taking the expectation over questions that we sample from a data set, right? So this could be just the GSM-8K grade school math dataset. We just take a question and we then feed that to the current model that we have to give us answers. And this is basically what this second term in the expectation is, this sampling from pi theta old, getting the entire batch O given the question. Okay, so we sample a few outputs, and then this is what we take the expectation over. And the advantage is then estimated by looking at each rollout, getting the reward for that, and then just normalizing it for each group. So let's say we sample 16 rollouts and we evaluate them with our rules-based reward. So each one is assigned a reward. And then to get a group relative, like to get it relative to the group, we just normalize it with respect to all the rewards that we got in the group. And this is what we use as an advantage. And if you think about it, it makes sense, because this is kind of the same as the advantage we used to use, because it represents if this trajectory, how much better this trajectory is than the one that we had before, right? That on average, like how much better it is compared to the average trajectory that we could have. Because this is basically what we do. We subtract the mean and we normalize with the standard deviation. And that's basically GRPO. Maybe we can go back to the slides once more. You can see these sums where it's just that the loss is summed over each. Well, if you look at the inner sum, it is just summed over each output and then over each group. So over each over each of the answers that we took. And we also have this KL divergence term, of course, because we're dealing with language models. Yeah, but that's basically it with GRPO. I didn't want to go too much into detail because it can get quite difficult. For example, the KL divergence is not calculated directly in practice, but we use an approximation. But this is not relevant to understand what GRPO is and why it works. It's just that we don't have the critic anymore, and that saves us a lot of compute and memory that we can now use to get more training done. Right, and this is how we get the advantage, of course. Great, and if you want to look at implementations, because I think the best way to learn is to just look at how it's implemented instead of just looking at the paper, I can recommend you take a look at the GRPO trainer, which is in the Hugging Face TRL library, which is currently being developed. So it is currently still rather inefficient, but it's improving very rapidly, and you should definitely take a look at that implementation. If you want a different implementation where GRPO is implemented as an extension of PPO directly, and it might help you to see how it relates to PPO, I can recommend you to look at the Volcano Engine RL library. It's by ByteDance, I believe, and it is implemented in that way. And lastly, you can also take a look at OpenInstruct, which might be more educational, which is, of course, the framework from Allen.ai. Right, that was GRPO. Let's now talk about the rules-based reward. So the thing here is that the reward is not learned. Many people are calling this RLVR, so reinforcement learning with a verifiable reward, to differentiate it from RLHF, which stands for reinforcement learning from human feedback. Because in RLHF, what we do is we estimate a reward model, we fit a function basically by looking at human preferences. And what is a rules-based reward then? Well, it's just a series of if statements, and it is dependent on the domain. And what DeepSeek found is that it is not that hackable. So you can't really reward hack that easily if the reward is grounded in certain rules. Like, for example, if the ground truth of a question is a significant part of the reward. It's very difficult to reward hack, whereas reward hacking a neural reward is pretty simple, especially if it's not on the domain that it was trained on, if it's out of distribution. Right, and DeepSeek's reward, as they describe in the paper, is just a combination of an accuracy reward and a format reward. So the accuracy reward is just, okay, is the answer that the model gave us correct? If so, we give it a higher reward, right? We add some positive number to the total reward. And then also is the format, right? For the format reward, is the format upheld? The one that we told it. So for example, that it should wrap its thinking in special tokens, in a special thinking start and thinking end token, and yeah, stuff like that. You can define in there, and then the format reward is gonna give you a little bit of a reward if it upholds the structure that we wanted to have. And maybe for some visualization, this is how it could look like. So you have this accuracy reward, which takes in the response from the LLM and the ground truth, so the true solution, and it does some check. Of course, in practice, you would not just check for equality, but you would have some scheme to extract the answer, the final answer, so the number, for example, in a math question, or whatever, and then compare to the ground truth. But in this case, we just do a simple equality, and we basically return 1 for our accuracy reward if it is true, and otherwise we return 0. And for the format reward, we just give our model a reward of 0.5 if both the thinking and thinking tokens are in the response, and otherwise we don't give a format reward. It's just 0. And then the total reward is just the sum of these different rewards. And this is what is meant by rules-based. You can have multiple rules, multiple rubrics, as some people call it, and just add them all together. And of course, that can be as granular as you want it to be. You can really go wild with it and experiment. It's pretty much an open question right now, what the best way is to design such a rules-based reward. Let's take a look at this graph, which is something that occurred during the training of DeepSeek R1.0. Let me remind you that DeepSeek R1.0 refers to the model that was trained with just the reinforcement learning with a verifiable reward for code and math on top of the DeepSeek v3 base model. And as you can see in the training, later on in the training, the longer the average response was, which is an interesting emergent behavior, because DeepSeek said in the paper that they did not penalize or encourage the model to think for longer. It just realized that it gets a better reward, and it is more often accurate. The response that it gives is more often accurate if it has more time, more tokens to think, which is quite interesting if you think about it. So this is something like emergent behavior here. It was not taught to think for longer. It just decided that, or it learned to do that. Also, another case of something that many people called emergent behavior is this aha moment in the reasoning trace. So as you can see, there's a question, a math question, and the LLM responds starts with the thinking token, and then it just thinks about how to answer this question. And in the middle of this reasoning trace, it just says that which is highlighted in red. It says, wait, wait, wait. That's an aha moment I can flag here. Let's reevaluate this step by step. And then basically what it does is it reevaluates and self-corrects, or at least tries to go down a different path on its own. So this was also not trained. Of course, it is possible that something like this was in the pre-training corpus. It's quite natural to have something like this on websites like Reddit or Stack Overflow. When those were scraped, maybe this behavior was latent somewhere. But here it really emerged in this, in trying to come up with an answer and with reasoning for the question at hand, which is also quite interesting. Let's talk about the reproductions, because a lot of people are currently trying to reproduce it, because of course the model weights are open with an MIT license, and also there's a technical report, but naturally they did not release the code that they used, right? Not their training pipeline, not their data curation pipeline, and so on, which is quite sensible. And so there were a lot of people, and there are still a lot of people trying to reproduce it to make it open. Here's like the three most notable ones in my opinion. On the one hand, we have TinyZero, which just aims to reproduce R1 0, so just the base model and then the RL, which is quite popular. Then there's also RayGen by Zihan Wang, and he's quite notable because he started his PhD, as far as I know, recently in a US university, and he was part of DeepSeek just recently, so he might have some insights from his time there. So that's definitely someone you should keep an eye on. And lastly, there's also by Hugging Face a project to get Open R1 going, which is like a complete pipeline from everything for the complicated R1 model, not just R1 0, which is just the RL. So Hugging Face wants to do everything that they did in a technical report, this multi-stage process with the SFT and rejection sampling and so on. So that is something that's still developing, and if you're looking to contribute, it's definitely something that you should look into if you're interested in that stuff. Let's also talk a bit about the impact this might have on startups. So this is the first time that an open source model is actually competitive with top models. Of course, O3 was recently released, and there are some mixed reviews on whether it's worse or better than DeepSeek R1. There are also some people that claim that O1 is better than R1, so the older reasoning model, and it's more of a vibe thing right now. It's not really an exact science, but at least R1 is in the same ballpark, and that is also something that is quite a new development, that an open source model is on that level. And that also means that the underlying LLMs are commoditizing, because now you don't only have to use either Anthropic's or OpenAI's API. You can also either self-host and use R1, or what you can do is you can find a provider that hosts R1 very, very cheaply as is possible, and just choose that. And you can always just change the underlying model pretty easily. So that is quite good for those who are building on top of LLMs, because they now get a choice which LLM they use, and that should drive down the prices, which is of course something that almost always happens when commoditization is happening. But it also means that branding, user experience, familiarity with a product becomes much more important than just the LLM that is powering this product, which is also something to keep an eye on. Then it also means that a building on top of LLMs is becoming a much more robust business model. So for a few years now, people were decrying a lot of founders as building nothing but a GPT wrapper that can easily be destroyed whenever OpenAI wants to make some money by just building a better product and competing on price because they own the underlying model, and because that product is just a wrapper around GPT. And that is from a time when the GPT series was basically the only thing that you could use in the first place. And now that we have R1, this obviously changes the game, and it's a lot less precarious to be a GPT wrapper now, because you're much more than that. You're just an LLM wrapper, but you get to choose which LLM you use as your underlying model. So we looked at how DeepSeek was trained, what the key innovations were. We looked at what impact it might have on the startups, and we looked at what impact it did already have on policy and the stock market. And now I want to wrap around to the beginning, which was, okay, is this another Sputnik moment? There were a lot of journalists already talking about and comparing DeepSeek to Sputnik and saying this is indeed a Sputnik moment. And most of them just equate a race to AGI with the space race, which is quite interesting, of course. And there's obviously a race to AGI going on right now. But on the other hand, there are a few things that that make it seem less like less of a good comparison. For example, DeepSeek was not unknown. So first of all, DeepSeek, yes, the company is Chinese, but it is not state-sponsored. At least it wasn't until the release of this model. So it's not really a country competing against another country. It's just a company competing against other companies. And DeepSeek was already well known among those who were paying attention. There are a few people on X who were paying attention to DeepSeek almost 2 years ago. Or if not quite 2 years ago, let's say 1.5 years ago. So it was nothing that shocked us. The only thing that shocked us was the reaction to R1. Also, Sputnik was, and the space race technology in general, was mostly kept secret and hidden from others, while DeepSeek released the model weights plus a pretty detailed technical report and gave us an MIT license to further work with it, work on it, and improve upon it. So it is definitely not some cryptic technology that we just don't understand how it works. It is they're quite open about how they achieved that. Also, the US is not really lagging behind. So O3, as I said, was teased in December, and the mini versions are already out now to everyone. And a lot of people are saying that O3 is on par with R1 in many domains. Well, others are of course saying something else, but it is quite clear to everyone in the field that the US labs are not lagging behind. They are probably pretty much on track with the scaling laws. It's just that they didn't release yet to maximize competitive advantage, or for whatever reason they might have. So where does this lead us? Is this another Sputnik moment? Well, I don't really think so. And to just borrow from the motto that DeepSeek has, maybe it's not a race, or it's not a competition between countries like the US and China, or the West and China. It's more of a competition between open source AGI and closed source AGI. And in this case, DeepSeek is definitely, at least for now, on the side of open source AGI. And I believe that they just want to push the frontier and, as they say, unravel the mystery of AGI with curiosity. And I think that's a wonderful point to end this talk. Thank you all for watching. And maybe think about what you can build with R1, or what research you can do to improve reasoning models. Thank you very much.